This probably looks like a terrible idea if you're new to this channel, but if you're not, you already know where this is going. We're finally building another cargo bike today. I've built quite a few cargo bikes on this channel already, and most of them were fairly large, except for this one. But today's project is different from all of those, because this one is about pushing compactness as far as possible, but without compromising on the core functionality that makes a cargo bike useful in the first place. The goal was to come up with a design that fits into a regular bike shed or an elevator and feels more or less like a normal bike when you're not carrying anything, and achieving that while still enabling it to carry significant loads when you do need to is a pretty interesting design challenge that involves making the right compromises. Most of the critical decisions were already made way before I started cutting metal, so let's jump into CAD for a second so you can see what I'm actually trying to build today. For most of my previous builds, I used a 20-inch wheel up front and either 26-inch or 28-inch in the back. But for this one I'm going even smaller, because reducing the wheel size is one of the easiest ways to shrink a bike without losing cargo space. So in this case the rear wheel is going to be 20-inch and the front is just 16-inch, which is about as small as I'd go on a bike for adults. Going this compact always comes with some downsides, because smaller wheels do affect ride quality, so this isn't about pretending there are no compromises and rather about setting priorities. As usual, I'm starting with the donor frame for the rear triangle because it saves a ton of work, which is why you just saw me cut into a perfectly functional bike frame. And while that's already considered blasphemy by a lot of bike nerds, I'm going to do something that's even more weird by using a 26-inch frame and adjusting the geometry and some other things so that it works with a much smaller 20-inch wheel. This might seem like a strange decision at first, but it actually solves several problems at once, and I'll explain that in a bit more detail later on. The most important feature on this bike is going to be this folding basket. I'm going to be building two foldable side panels that attach to the frame via some custom joints, allowing you to significantly reduce the width of the bike when parking or riding empty. Inside the basket it fits a standard 60 by 40 cm Euro crate, so it still offers a really generous amount of cargo space, and despite that it fits pretty much anywhere a normal bike fits. Like my last build, this one also has electric assist, but since it's based around a standard frame, it also works perfectly fine without a motor. Steering is going to be done with a simple rod mechanism again, because it's easy to make and basically maintenance free. And the version of the bike I'm going to be building today will be made mostly from aluminum, as well as some machined bits and quite a few 3D printed parts. But if you don't have those capabilities, you can absolutely build a steel version of this, and you don't need all the fancy tools I have here either. Many of the techniques and workarounds I showed in my older DIY focused build still apply to this design as well, because they're actually quite similar. So today we're going to be making the entire frame and the steering system, and then part 2 will come very soon after and cover everything else. And as always, I also made a set of plans for this bike. I'll talk about that some more in a bit, but for now let's head over to the shop and start touching metal. So here's the donor frame I'm going to be using. As I mentioned, this is actually a 26-inch mountain bike frame that I'm going to modify to work with a much smaller 20-inch wheel. One of the main reasons for that is that finding a suitable 20-inch frame is really difficult, because up until recently 20-inch wheels were almost exclusively used for folding bikes and kids bikes, and neither of those are sturdy enough for this purpose, while mountain bikes like this are actually built to take a beating. As you can see, someone clearly painted over this at some point and then tried to remove that paint again, but none of that really matters because we're cutting it apart anyway. I'm starting by removing the entire front triangle with 2 cuts at the bottom bracket and the seat tube. And the next part is always a bit tedious, because now we need to remove the leftover welds and the tube remnants in those areas. I usually start with the cutting disc to get rid of the bulk, then switch to grinding, and as I get closer to the actual tube I gradually move to less aggressive tools like a hand file, because the most important thing here is to avoid removing material from the tube we want to keep. And if you're only using an angle grinder for this, it's extremely easy to gouge the tubing by accident. The bottom bracket area is even more tricky, so here I like to use a die grinder for the rough work. These carbide cutters remove material pretty quickly, but they also like to bite in and walk around in the cut if you're not careful. After that, it's back to the flap disc on the angle grinder, and then for the final cleanup I'm using strips of sandpaper since they conform nicely to the curved surfaces. With the bottom bracket shell cleaned up, I'm gonna remove the old brake bosses next. These were extremely common on frames from this era, but since I'm converting this frame to disc brakes, they're not going to be needed. It also doesn't hurt to just leave them, but it's going to look much cleaner without those. Once that's done, I can finally strip the paint. My blasting cabinet helps a little bit here, but the original powder coat underneath the respray didn't want to come off in some areas. So I also had to use paint stripper and a few other methods. It's not super interesting to watch though, so here's the finished and fully cleaned up rear triangle. Now we can prepare the tubing for the actual frame. For the Downtube, I'm using a 50 by 3mm aluminum square tube. That's pretty overbuilt for such a short bike, and I could have most likely gone with 2mm walls easily, but I wanted this one to be extra sturdy, and the thicker walls will also allow me to cut threads directly into the tube later, which is really convenient. I'm marking the cuts out with a digital protractor here. These only cost around 10 to 20 bucks, and they are extremely useful for this kind of build. And to rule out any dumb mistakes, I usually mark all 4 sides before cutting, at least when I'm building bikes. The nice thing about miters is that the cutoff piece already has the correct angle, so I can just reuse that and only need to make one more cut. And the last piece here only needs a straight cut. For the long steering tube, I am once again using a pretty thick wall tube. This is a 40 by 3mm round tube, which conveniently fits standard headset cups. So all I need to do right now is to cut it to length. For the front head tube, things are a bit trickier because I'm using a different headset standard there. This one is a 48mm tube that I'm going to enlarge on the inside for 44mm headset cups. But I'm not cutting it to final size yet because I'm going to manually ream it after welding. Next I'm prepping this little rectangular piece that allows me to mount the down tube below the bottom bracket, which is the same thing I did on my last build. This does 2 things at once. First, it lowers the center of gravity of our cargo, which considerably improves the handling, and it also allows us to neatly tuck the motor inside of the frame here, rather than having it hang below the bottom bracket, which is how it's actually intended by the manufacturer. It's simpler than it looks. It's just a piece of 30 by 50mm tube that gets a straight cut and a round miter, and these hole saws usually bottom out on deep cuts, so I'm removing the last bit manually. For the top tube, I'm going to reuse the one from the donor frame. After cutting that off, I'm now removing the old cable guides because they're kind of ugly and not suitable for disc brakes anyway, so I will later replace those with a custom solution. Trying to cut this off with the grinder without hitting the actual tube seemed a bit too risky, so instead I figured I'd just grind it off. After grinding this thin enough, it was actually possible to just sort of peel it off, which was oddly satisfying. At this point all the main tubes are roughly prepared and you can already start to see the frame taking shape here. The next step will be to cut all the miters so everything actually fits together properly. I'm starting with the long section of the downtube, which just gets a straight 90-degree hole. And by the way, most of these cuts can easily be done on a normal drill press, which is how I use this mill most of the time anyway. Next up is the miter for the front head tube. In this case it fits perfectly into the down tube because both tubes have almost the same width, so we end up with a nice clean front end. Then I need to miter the top tube, which is a bit trickier because it gets miters on both ends, so we need to make sure they're properly aligned to each other. With a round tube, this means we need some kind of reference, so I'm scribing a straight line along the tube exactly at half its diameter using a height gauge. With this reference line I can now clamp the tube into a tube lock. I made these ones myself, but you can also buy them and you can even 3D print them, and those work pretty well as long as you remove them before welding. The tube lock also has its own center line, and once aligned with the scribed line on the tube, it essentially lets you treat a round tube as if it was a square tube, which also makes holding the tube in a vise for cutting a lot easier and safer. And to set the cutting angle in the vise, I'm using my little miter box with the jerry-rigged 9-volt battery again. Since we're shortening the top tube significantly, I didn't bother removing the cable guides on this side because I figured I could just cut them off together with the excess. But I made a little oopsie here. It looks like I didn't tighten the chuck properly because the hole saw decided to make an escape, and considering how much I abuse these things, I can't even blame it. With all the cuts done, I'm doing some finishing steps now, mostly filing or grinding off very thin areas. For example, since the down tube and the head tube have the same width, the wall thickness converges towards 0 at the ends, which leaves only a really thin edge that would melt away instantly if I try to weld there, which can really throw you off. I'm also chamfering the edges for better weld penetration, and while I was at it I figured I'd also chamfer the long edges as well, just to make the tube look a bit less boxy. This little air-powered chamfer mill is super handy for this kind of thing, because with a bit of practice it produces very clean, even chamfers, and these are actually not that expensive. Now that all the parts are ready, I'm setting up the frame jig. I custom built this jig to work with my welding table for a wide variety of frames. And if you want to know more about this particular jig, I talk about that in more detail in a previous video that I'm going to link in the description. But that being said, you can build a perfectly functional jig for this kind of build using nothing more than a long piece of aluminum extrusion and some screws, all of which is reusable afterwards, and there's actually a full chapter about this in the plans, including a material list. First I'm setting the angle of the C-tube here, and this is probably a good place to explain what I meant by adjusting the geometry in the beginning. So if we installed this donut frame in the orientation it was originally meant to be in, we'd end up with a rear axle much higher than we actually want. In combination with the smaller wheel, this would result in the whole frame dropping down in the back, which would look something like this. This would ruin our entire geometry and make the bike basically unrideable. So instead what I'm going to do is to actually tilt back the frame by a few degrees, which results in a flatter C-tube angle and a smaller BB drop, which is the vertical distance between the rear axle and the bottom bracket. This way we're basically pretending that this is a 20-inch frame, and it works surprisingly well for this purpose. The flatter C-tube angle is actually beneficial in this case to make the frame scale better for both shorter and taller riders, since the distance between the handlebars and the seat increases at a greater rate the further you pull out the seat post. At the same time, a 26-inch frame does give us a slightly longer wheelbase than we could theoretically get away with if we tucked the rear wheel all the way against the seat tube here. But you really don't want to do that because it would mess up the whole weight balance on the bike, with the rider basically sitting directly on top of the rear axle, which feels weird to ride and puts a lot of stress on the rear end, while having almost no weight on the front end, which is already a problem with long bikes like this. So in this particular spot, making it as short as possible would actually be a bad decision, and the 26-inch frame in this position actually gives us a really sensible overall geometry. The second part of the jig here holds the long steering tube, which first has to be inserted into the down tube. And to keep that level, I made some simple adjustable standoffs. Then there's the little connecting piece here, which I actually remade off camera from some thicker tubing, so that's why it looks a bit beefier now. Once everything is in position, I can start checking the fit of the top tube, which is already looking pretty good. But I'm not going to weld anything inside the jig yet. Since the down tube is made from square tubing, we don't actually need the jig to weld that, as long as we have a reasonably flat surface to do it on. So I'm placing those parts directly on the table and welding them into a sub-assembly, and afterwards they can go back into the jig as a single piece, which makes this whole process a lot easier overall. As always, I'm using an AC TIG welder, and this cheap import welder I've had for almost 10 years is unfortunately on its last breath. The high frequency start is really struggling to strike an arc at this point, which is why you're hearing that stuttering sound throughout the build. And while I don't want to blame the tools, I think this also contributed to some of the welding issues I had later on. So if any welding companies are watching, you know where to find me. While you're watching these welding shots, I figured this is a good moment for the mandatory self-promotion part of being a content creator, but I'll try to keep this short. As mentioned in the beginning, I once again made plans for this project, and they're even more detailed than on my previous builds. Of course, they include detailed drawings of every component, and you also get a material and parts list for both the steel and an aluminum version, plus a lot of extra information. There's detailed guidance on how to choose a donor frame, how to make sure your geometry comes out right, various common mistakes to watch out for, suggestions for bike parts, assembly notes, workarounds if you don't have a fully equipped workshop, and even a section on converting the frame to disc brakes. And as I said, you'll also find the full plans and a parts list to build a simple frame jig that can also be used for other builds. All in all, it's over 30 pages of drawings and explanations, and it also includes the full 3D CAD model you saw in this video for reference. So if you're thinking about building your own version, you'll find the link in the description. And while we're at it, I've also reworked my Patreon a bit. There are some new tiers with updated benefits, and I'm planning to be a lot more active there in the future. We're starting with an exclusive deleted scenes video from this build, basically all the stuff that didn't make it into the final cut, and this is where you will also find more regular progress updates between builds. So if you want to support the channel there, I'd really appreciate it. And with that out of the way, let's get back to the build. Welding the sub-assembly went well, and it's now in one piece, but before putting it back into the jig, I need to fix something on the donor frame first, which unfortunately turned into a bit of an ordeal. Something that's a little annoying for this type of build is that bike frames almost always have these vent holes in the bottom bracket shell, and the C-tube is also not fully welded at the bottom because that part was originally inside the old Downtube. Since I'm not connecting a new tube here, I need to finish that weld and close the hole, so I made this little half-moon shaped plug. At this point I unfortunately ran into a ton of welding problems, most likely caused by dirt that was still trapped under the remains of the old weld, even though I cleaned it as thoroughly as I could. Aluminum is extremely sensitive to contamination, so even a tiny bit of grease or embedded metal can cause issues, which is one of the reasons I would recommend beginners to start with steel. I eventually got the weld under control, but I still didn't feel completely comfortable leaving it like that, so I ended up grinding the first weld flush and adding a gusset on top of it in this area just for peace of mind. This should make it highly unlikely for the C-tube to ever separate from the bottom bracket, and while I admit it's not the prettiest thing ever, this will be barely noticeable once everything is assembled. Now the Downtube assembly can go back into the jig and I can set up the front head tube using its own fixture. The top tube goes in as well, and now I can place the first tag welds between the main tubes. And one of my favorite moments in any frame build is when you can finally take it out of the jig in one piece and it actually starts resembling a bike. At this point I usually do a quick geometry check by installing a fork and some wheels just to rule out any obvious mistakes, and it's all looking promising so far. With that confirmed, I can continue to run the actual welds now. Once all the main welds are done, the frame goes back into the jig one last time to check for welding distortion, and that's really where a jig shines. It's not just during assembly, but because it gives you an accurate reference to see how much things move during welding. So as expected, the front head tube is a little bit out of alignment, which is very common on builds like this. To fix this, I can measure the distance from the table at the bottom bracket, which is my 0 point, and then compare that to the distance on the other side of the Downtube. After that, it's mostly a matter of carefully pushing and pulling until it lines up again, which I also double check using the cones on the fixture. The end of the steering tube was also slightly off, so I corrected that the same way, and the seat tube was looking fine, so it should all be fairly straight now. The very last step here is cutting the front head tube to its final size using a reaming tool. As mentioned before, I left this tube slightly undersized before welding because the head tubes will often distort when welding and go a bit oval, especially here where the weld is only on one side. So by reaming it afterwards, I can guarantee that the headset cups will sit in a perfectly round hole. Now that the frame is welded and aligned, the next major task is building the steering system. But before we get to that, I just want to say a quick word about today's sponsor. I've got another 3D scanner from Revopoint to show you, and before you skip this, it's actually quite relevant to our topic because it can help me design more bikes. Today we're looking at the MetroY Pro. This is from their professional lineup and extremely capable, but it's a lot more affordable than the Trackit I tested recently, which is their flagship scanner. Having used both, I'd say the MetroY hits a really nice sweet spot in terms of price versus performance, while delivering very similar scanning speed and quality. It's compact, easy to use, and gives you a lot of flexibility with 5 different scanning modes, including a fully automatic one. And what I like most is that you can either run it cabled for longer sessions or completely wireless. So coming back to bike building, I want to try scanning the upper swing arm of this full suspension frame here. I've been toying with the idea of making a custom version of this that uses modern through axles, which means designing new dropouts and doing a full rebuild while keeping all the mounting points exactly where they belong. In other words, this is a classic case of reverse engineering. This part has a very complex shape though, and measuring it and rebuilding it in CAD by hand would take forever, but scanning it with the MetroY Pro only took about half an hour from start to finish. And it gives me confidence that the model is spot on, since this scanner is able to produce scans that are accurate to within less than 0.5 of a millimeter. Just like the Trackit, it captures data very quickly at up to 60 FPS, and you don't even need markers on the part itself. In this case, I just put a bunch of markers on my cutting mat here, and the tracking worked perfectly. After scanning, I ran everything through the Revopoint software to clean up and refine the data, and eventually I ended up with a pretty much perfect model. I can now export this and use it as a reference in something like Fusion to make sure all the mounting points and functional surfaces line up perfectly when I redesign anything. If you're interested in the MetroY Pro or the non-Pro version, which is even more affordable, you can find links in the video description. And with that, let's get back to the build. Unlike the cable steering I built for the last bike, this one is going to use a classic steering rod mechanism again, simply because it's much easier to make, needs almost no maintenance, and for a bike this short, the steering angle advantage of cables isn't really worth the added complexity. If you've never seen this kind of setup, it's pretty straightforward. At the bottom of the steering shaft there's a small arm that moves the joint, which then moves the steering rod, which finally moves the fork with the ball joint. The bend is there so it can clear the wheel, and the custom rear joint limits movement to 2 axes. I'm gonna start by making the steering shaft, which is made up of a long tube, and the steering arm at the bottom, which is fairly easy to make. This is cut from some aluminum flat bar, and after drawing some layout lines, it gets a bunch of holes to mount the joint in different positions, so you can fine-tune the steering later. And after that I rough cut the outside shape on the bandsaw and cleaned it up on the belt grinder. Next up is the steering shaft. I'm starting with the 30mm tube here and turning the upper end down to 1/1/8 inch, so it fits the standard stem and headset. The lower section only gets turned down slightly because 30mm is actually exactly the size needed for the crown race. But since that part is pressed on, I only leave the last bit at full thickness, so the race can slide down and then seat properly at the end. And since this thing is too long to turn in one go, I also flipped it over at some point to finish the lower part. So with everything done, I can attach those two together now. The nice thing about these welding cables is that you can also use the sides to hold stuff. So I can clamp the tube to the side and place the arm on top, which gives me a perfectly comfortable welding position and helps to keep everything square. After that I can press on the crown race, which is easy in this case because most modern headsets use a split crown race that slides on easily without needing to be hammered on. And by the way, if you don't have a lathe, you can do a workaround here by sacrificing an old fork by removing its legs and welding a steering arm to its crown and then extending its steerer to get something that serves basically the same purpose. Now I'm installing the headset cups. The proper way would be to use a headset press, but a rubber hammer usually works as long as you're careful. With the cups installed, the shaft can now go in along with the stem on top. And that completes the first half of the steering assembly. Next up is the steering rod, which is basically just a tube with a bend in it. People often ask why I don't bend tubing more often in frame building, and the short answer is that bending tubing is far more complicated than most people assume, and it requires very expensive machines once you go past a certain diameter. But for small tubes like this one, you can get away with using something like this simple manual bender. These are usually used by plumbers to bend copper pipes on site. That's also the reason they are quite common and therefore affordable. I actually got this one used for just 20 bucks, and as usual, the first thing I did was take it apart and modify it, which I talk about in more detail on Patreon, because that would be just too much of a tangent here. Since this part only has one bend, the exact bend location isn't critical as long as there's enough straight material on both sides to trim afterwards. Unfortunately, these cheap benders don't have any kind of angle scale, so I have to check it manually and slowly work up to the angle I need. Once the bend is done, I can trim the rod to final length and insert a machined plug on one side that will later be welded. Then the other side gets a slot, and you'll see what that's for in a second, but first let's move on to the joint. The joint itself consists of 3 parts, 2 aluminum blocks that form a hinge and a clamping collar that holds the rod in place and allows for length and angle adjustment. Later on I actually changed this design slightly and simplified it so that you don't actually need that clamp, but I'll explain that in a second. For now, let's just make the 2 joint bodies, which involves a bit of machining in my case, but as with the other parts, it's not strictly necessary. So the 2 blocks here form a 2-axis joint, which means the steering rod can move on 2 different planes. Now you might be wondering, why would we even need 2 dimensions, because it seems like a single axis of rotation would be enough down here at the steering arm. But if you look at it from the side, the steering rod does actually move up and down a little bit when you steer, which is caused by the steering angle of the fork. Now we could actually use a ball joint on both sides to save a bunch of work, and I've done builds like that in the past. But while that does work, the problem is that it would also enable the steering rod to sag downwards and also bounce around when riding on bumpy surfaces, which is not only annoying, but it also wears out the joints very quickly. As for the finer details of the joint, I think this design is a lot more elegant than what I've done in other builds, because it uses 3D printed bushings. Before, I've always bought or manually machined plastic bushings, but being able to print them on demand is incredibly convenient. I printed the bushings slightly undersized on purpose and then finished them with a reamer, because even though modern printers are pretty accurate, getting a perfectly sized hole out of them can still be a bit of a pain, and this method only costs a few extra seconds. And in case you don't know what a bushing actually does, their job is basically to isolate wear. Instead of wearing down any of the important moving parts like the aluminum or the screw that's gonna go in here, the bushing sits between the moving surfaces, so you only wear out the bushing, which is easily replaced, and the other job of the bushing is to reduce friction. Another improvement I made over older designs is that I'm using shoulder screws here. Previously I used normal screws with lock nuts and adjusted the preload manually. That works, and the parts can be found in any hardware store, which is handy. But shoulder screws are simply a much cleaner way engineering-wise. Unfortunately, they're a little bit harder to find, and at the time I filmed this, my actual screws were stuck in the mail, so I printed these yellow ones purely for demonstration purposes. The cool thing about these is that unlike regular screws, they have this smooth section, which is called the shoulder, and its surface is very accurate and has a defined diameter and a defined length. And if you design your parts around that, you can just screw these in without doing any adjustments, and the joint tightens perfectly without binding and with zero play. The last part we need is this clamping collar. As I mentioned before, I later changed this design because I realized it's a bit overkill. A simple threaded rod would also work just fine to connect the joint and the steering rod. So for the version in the plans, I actually simplified this, since making the clamp is really kind of unnecessary. With all the joint parts prepared, we can now do a test assembly. As you can see, I've received the proper steel screws at this point, but the bushings are still just PLA placeholders for testing and will eventually be replaced with nylon versions. But it looks like everything is working fine so far, so we can move on to the last part of the steering. To install everything, we just need to add a small tab on the fork, which is fairly easy to make out of some steel flat bar. As for the fork itself, this is just a generic 16-inch steel fork I found on eBay. I assume this is for a folding bike, but since it's made from steel and it's so short, it's very sturdy. There aren't many options for 16-inch forks, especially with disc mounts, so just like on the frame, I'm cutting off the V-brake bosses here, and I will then be adding disc brake tabs to this in part 2 of this build. For now I'm installing it like this so I can do a test assembly. Instead of a stem, which we obviously don't need on this end, I'm using a clamp, which can be either a seat post clamp or you can also make one by cutting apart an old stem. And on the other end of the steering rod I'm now installing a ball joint with high strength Loctite because I don't want that to twist loose. You can also get ball joints that have an outside thread, by the way, in which case this step isn't even necessary. And once everything is bolted up, the steering system is essentially finished. So at this point you might be thinking, Phil, how can you possibly make another video about this, since the bike is basically finished now, right? I fell into the trap of thinking that myself many times before, but it's really easy to underestimate just how much work is left here, since all the small details really add up, and as you know, details are kind of my specialty. So overall, at this point, I'd say we've only done about 40% of the total work, and the really interesting part is still coming. Before finishing this in part 2, the biggest task is building the folding basket. But there's also many other additions, like making the folding joints, a kickstand mount, adding disc brake mounts, a cargo bed, cable guides, and many other details. And then there's of course the assembly, wiring the electric components, and many other small problems that still need solving. And of course showing you the final result, so you can look forward to another hour of building very soon. So if you don't want to miss that, make sure to subscribe. If you got any questions, write them in the comments. Check out my Patreon, maybe buy some plants. Make sure to drink enough water. Merry Christmas, Happy New Year, and thanks for watching, and see you then.